Good morning, everyone, and welcome to the fifth and final day of the Inorganic Ventures Virtual ICP Conference. I'm Leslie Owens, and today I'm going to be your moderator. Just a quick housekeeping reminder, please put your questions in the Q&A box at the bottom of your screen. We'll address these in our roundtable session at the end of today's presentation. Let's get started. Our first presenter is Autumn Phillips, and she will be focusing on heavy metals testing for cannabis and hemp. Autumn is an R&D chemist at Inorganic Ventures with experience in bulk scale manufacturing, reactions, and purification performance and improvement. She also has several years of experience in manufacturing custom CRM products. Autumn received a BS in biochemistry and a BA in chemistry from Virginia Tech. Take it away, Autumn.
Hello everyone, and thank you for joining us. In this presentation, we'll be going through a heavy metals analysis using ICP for cannabis or hemp testing. So the big four are arsenic, cadmium, lead, and mercury. We're going to start off by going through some of the instrumental issues that you may encounter in your analysis. Then we're going to talk about your working solutions and how you can plan for maximum stability and compatibility of those. Then we're going to go through some sample prep techniques and strategies to help you make sure that you're not having any loss of analytes or any other issues. And finally, we're going to go through some of the products that IV has to offer that may help in your analysis, as well as our technical support resources. The first heavy metal that I want to focus on is arsenic. So a lot of people, when they think about arsenic, they think about arsenic plus 3 and arsenic plus 5. But in actuality, arsenic actually has no cationic chemistry. So it's going to exist as arsenite will be what you think of as arsenic 3, and arsenate is what we think of as arsenic 5. So this does matter when it comes to analysis on an ICP, because we found that arsenate and arsenite actually do have different signals on the ICP OES. So there are some inconsistencies in the literature about which one gives higher intensities, but here at IV we have seen that arsenic 3 actually gives higher intensities than arsenic 5. So you can see the difference in intensities demonstrated here. This is actually an analysis that we performed on one of our instruments here at IV. The green peak that you see there is a 10 ppm standard of arsenic 3, and the purple peak is a 10 ppm standard of arsenic 5. So you'll see that there is a slight increase in the signal for arsenic 3 versus arsenic 5. And we found this consistently to be about a 3 to 6% higher counts for arsenic 3 versus arsenic 5. So this is going to be really important if you have different forms of arsenic in your standards versus your sample, because that could cause, a high or a low bias if they are in different forms. Another issue you may run into when analyzing cannabis and hemp, or any organic sample, deals with spectral interferences from carbon. When analyzing a hemp sample in-house, we noticed that our arsenic recoveries were coming up high on the 189 wavelength. We suspected this could be an issue with matrix matching our standards and samples. We had used closely matched acid concentrations, but we had not spiked any carbon into our standards, so we decided to run the experiment you see here. We first ran an acid blank and a 30 ppb arsenic standard, followed by the identical blank and standard with 1500 ppm carbon spiked into the matrix. As you can see, the acid blank with the carbon spike is reading as approximately 4.3 ppb arsenic, and the 30 ppb arsenic standard with the carbon spike is reading approximately 5.4 ppb high. This high bias was only observed on the 189 nanometer wavelength and no other arsenic wavelengths, so we were able to conclude that the high bias we were seeing was actually a spectral interference from the carbon. We then spiked all of our standards with 1500 ppm carbon to properly matrix match our samples and account for this interference. Another thing to keep in mind for your arsenic standards is the starting material type used for your arsenic. So this is going to affect the final form of arsenic in solution. Some of the common starting materials that we use here for arsenic standards are arsenic metal, arsenic trioxide, and arsenic pentoxide. So specifically with the arsenic metal, we have to keep in mind that we want to convert all arsenic to the same form. So when we react the metal in nitric acid, it first converts to arsenite or arsenic 3, but the oxidation with the nitric acid will slowly convert it to arsenic 5. So we want to make sure that it's all going to be an arsenic 5 in the final solution. So what we do is we heat it for a prolonged period of time, generally about 24 hours with concentrated nitric acid. And we've ran experiments to make sure that this will be successful in converting all of our arsenic 3 to arsenic 5 in our final concentrate. This table gives some recommendations on the wavelengths to look at for arsenic on both ICP-OES and ICP-mass spec. Generally, we recommend looking at the 189 wavelength on ICP-OES because this is going to be the most sensitive line. However, there is a chromium interference, so you want to make sure to check multiple wavelengths whenever possible to make sure that you're not seeing an interference at one line versus the other. One thing I did want to point out here for this presentation in particular, since we're looking at the big four heavy metals, is that there is a major cadmium interference on the 228 wavelength. So if you do have cadmium present, you want to make sure to use a different line for both arsenic and cadmium. Another thing I wanted to point out is that arsenic is monoisotopic, so if you're using ICP mass spec, you only have the 75 mass to look at. And also if you have chloride in any of your samples or standards, you're going to want to make sure to use a collision cell or helium or hydrogen mode to break up the argon chloride interference, as this is going to cause major issues for both arsenic and selenium if you're looking at that as well. That brings us to mercury. So the first thing you want to keep in mind for a mercury analysis on ICP is that mercury must be in the mercury +2 ionic form to achieve accurate ICP results. Another thing we want to keep in mind is that mercury is going to stick to plastic when it's contained in a nitric acid only matrix without hydrochloric acid. So many of your intro system components are going to be plastic, your tubing, your connectors, potentially your nebulizer and spray chamber, depending on what type of intro system you have. So you want to make sure to keep that in mind if you do have mercury in a nitric acid matrix, that it is going to stick to the plastic components. So we do recommend using as much glass components as you can for mercury analysis if you are using a nitric acid matrix, as this won't be an issue for glass components. So your initial analysis is not going to be affected by the sticking of mercury. You're probably going to still get maybe the correct results, probably the correct results, but for future analyses, you're going to have a lot of carryover effects from mercury because it will stick in your system longer. So we recommend using hydrochloric acid for your rinses, and if possible, also adding thiourea, as this is going to really help wash out that mercury quicker. So to avoid any of these issues with adsorption to plastic components, we recommend adding a little bit of hydrochloric acid to your matrix to prevent any sticking, as the mercury is going to be stabilized by the chloride. But as we discussed in the previous slide for arsenic, adding this chloride to an ICP mass spec analysis is going to cause that argon chloride interference for arsenic and selenium. So if you are analyzing the big four or selenium as well, you're going to want to use collision cell to break up the argon chloride interference. Under reducing conditions, mercury can form the dimer, mercury 2, 2+. The dimer can then disproportionate into mercury 2 plus and metallic mercury when introduced to chloride or other ligands in solution. This can cause major issues as the metallic form of mercury is volatile and will therefore have a much higher transport efficiency, causing extremely high results. If you're seeing mercury recoveries of several 100%, chances are you have reduced mercury species in your sample. On the other hand, if you're seeing low results, you could have issues with adsorption of the mercury to plastic containers or other plastic materials prior to analysis, or you could have had the dimer or metallic mercury present at some point in the solution, which was lost over time as the volatile metallic form. So this table gives the recommended wavelengths and masses for mercury on ICP OES and mass spec, along with the interferences you can expect to see at those lines. So an additional line you can use for ICP OES is the 435 wavelength. And then I also gave some additional masses for that you can look at for mercury on mass spec. So you can see that the 202 line has a tungsten interference. So if you do have tungsten in your samples, we recommend using the 201 mass. But on the other hand, if you have rhenium in your samples, there is going to be a rhenium interference on the 201 mass. So like I said, we do generally recommend looking at multiple wavelengths or multiple masses for all of your analytes to determine which ones are going to be free of spectral interferences to make sure that you're getting accurate results. Cadmium of the big four is probably going to be the easiest or have the least amount of issues for an analysis on ICP, but I did want to still provide the table to give you guys some recommended wavelengths and masses to look at for cadmium. And just a reminder, the 228 wavelength on ICP OES is going to have that arsenic interference. So again, if you are conducting an analysis of the big four, we recommend looking at other lines for both cadmium and arsenic. And then for mass spec, you are going to have the molybdenum interference at the 111 mass. So we recommend looking at the 112 and 114 masses as well to make sure that you're not getting any interferences on any of those masses. Lead is also going to be relatively straightforward for an ICP analysis. But again, here's the table for the wavelengths and masses that you can look at for lead. And the main thing I wanted to point out is that one of the masses for lead, the 204 mass, does have a mercury interference. So you want to make sure to look at some other masses if you are doing the big four analysis. One of the main issues that you may run into is actually the matrix itself, especially if you're dealing with a high salt matrix. In these cases, you may need to condition your cone by running a matrix blank through the system for a little while before analyzing the samples. But it may be better to just dilute your samples further to reduce the concentration of certain matrix components that could be causing your issues. Another problem you could run into is clogging of the nebulizer. We recommend contacting your instrument manufacturer to get your recommendations on appropriate introductory system setup for your particular analysis prior to running the analysis. This would include any total dissolved solids limitations for the instrument or the intro system components. And then high acid matrices may also cause increased corrosion on metal components of your instrument. So this is going to be a particular concern for hydrochloric acid. So we recommend reducing the hydrochloric acid if possible to prolong the life of your ICP as well as reduce the maintenance required. One thing we always recommend for any analysis on ICP, but particularly for a cannabis or hemp analysis, is matrix matching your samples and standards. So this is going to be really important for multiple reasons. So one of those is to account for any spectral interferences. So we demonstrated this with the carbon interference in the earlier slide with arsenic. Another thing you want to make sure to do is account for signal suppression from a higher matrix. So if your samples have a higher acid content than your standards, you're going to have these differences in the background signal. So you want to make sure to matrix match as closely as possible to get the most accurate results. Another thing that you may not think of as often is the actual physical properties of your solution. So these are all going to affect how your aerosol is formed, the surface tension, the viscosity. You want to make sure that those are matched in your standards to your samples to make sure that your nebulization efficiency is consistent. If you aren't able to completely matrix match your standards and samples, a really good option that we recommend is standard additions. So I've linked our webpage that gives you some tips on running a standard additions method here on the slide. So this is going to be a really good option because you spike your standard directly into your sample, so you're not going to have any of those matrix effects causing issues for the analysis. But it does take a little bit longer to do your data workup and your calculations. So definitely check out this webpage if you are having issues with performing a standard additions analysis. Another option we recommend is use of an internal standard, which applies a ratio to your analyte intensities based on the signal from your internal standard to correct for nebulization and plasma-related effects. There are several important factors to keep in mind when selecting an internal standard. First, you want to make sure the element you select is not already present in your sample. You also want to make sure that it will be compatible with all other components, will give a sufficient intensity at the selected concentration, and will not cause interference issues. Lanthanides are commonly used as internal standards, but these will have stability issues with hydrofluoric acid, so an alternative option will need to be used if HF is present in the sample. If you're using mass spec, you should select an internal standard with a mass similar to your analyte. So if you're analyzing multiple analytes, you may need to select multiple internal standards to cover the entire mass range. Ivy has a large selection of internal standards, which you can find at the link provided here. However, if you don't find what you're looking for, we can create a custom standard made to your specifications for elements, concentrations, and matrix when you submit a request for a custom quote using the link that I've provided here. Another important consideration for cannabis and hemp analyses is selecting an appropriate reference material to validate your method and make sure that you are getting the correct results for all of your analytes. So when selecting a reference material, you want something that is going to be very similar to your sample that has been well characterized for any analytes of interest. So analyzing the reference material in the same way that you are processing your samples is going to make sure that you're getting the correct results for analytes and also that no analytes are being lost during the sample prep or any other step of your process. Another really important thing to do is to run method blanks. So running a method blank is where you would process everything the same as you would your sample, except you don't add your sample. So this is going to make sure that you're not adding any contamination during the process, and it can help you identify where that contamination is being added. Another issue to keep an eye on is washout. So certainly of the big four, mercury is going to be your major culprit for causing washout issues or memory effects. So one thing that we recommend for ICP OES is running RBS 25, which is a surfactant. So we run a 2.5% by volume RBS 25 solution at the end of each analysis to prevent sticking. So what this does is it conditions the surface of your spray chamber, which is going to prevent any larger droplet formations, which are going to cause higher memory effects or more sticking throughout your analysis. So we don't recommend using RBS 25 for mass spec because of the very high sodium content, because that's going to cause probably more issues than you're fixing when you run it on a mass spec. Another thing that we recommend doing is replacing your PVC tubing or your peristaltic pump tubing. if you're seeing high carryover or high washout, as this is going to be the major culprit for where those sticky elements are going to accumulate. For mercury, we do recommend a hydrochloric acid and thiourea rinse, as this is going to really help get that mercury purged out of your system. And this is also going to be a really good option for gold. So if you're using gold to stabilize your mercury, that's going to help rinse out both mercury and gold. If you don't want to use hydrochloric or thiourea, you can use ammonium hydroxide. So it's going to be a 1 to 5% solution for both OES and mass spec. Another thing that you want to keep in mind is that if you're using triethanolamine to neutralize hydrofluoric acid in any analyses that you're running at a similar time to your mercury analysis, because the T can actually reduce mercury to the metallic form in your waste container, and that can actually cause mercury to the volatile mercury to come back up your lines and cause your results to be skewed for subsequent analyses. So if you do have that in your waste container, just make sure to dump that or switch out your waste container before performing your mercury analysis. That brings us to our working solutions. So the main thing you want to keep in mind for a Big Four analysis is you want to keep your working solutions in acidic matrices. These elements can all form insoluble precipitates in a neutral or basic matrix, so you want to make sure that you're keeping those in acid. But one thing to keep in mind for lead is that it is a common contaminant in pipette tips as well as acid reagents, particularly nitric acid. So you want to make sure that you're using the appropriate grade of acids and making sure that you maybe leach your pipette tips or other materials that you're using to make sure that you're not introducing any contaminants. Another thing to keep in mind with lead is that it will have issues with chromium-6. So this is not going to be an issue if you do keep your solutions in acid matrices, as the chrom-6 is going to be converted to chrom-3 under acidic conditions. Another thing is if you're using sulfuric acid or any other form of sulfate, this can also cause a precipitate with lead. So if you do need to add sulfur to your standards, one thing we recommend as your sulfur starting material is methane sulfonic acid. This works really well for us in combination in our standards with lead, and it doesn't have many issues with other elements or components of your solutions either. So that may be a good option for you if you need to add sulfur. Another thing to avoid is tartrate, because this can reduce mercury to the metallic form. So this becomes an issue for us when we have antimony in our solutions. So antimony can be stabilized with either hydrofluoric acid or tartrate. So if we are adding any antimony, we make sure to use the hydrofluoric acid stabilized starting material rather than the antimony stabilized with tartrate to avoid any of these issues with mercury. Another issue you can run into deals with the solubility of arsenic, lead, and bismuth when combined at high concentrations in your solution. So you may need to increase your nitric acid concentration if you do have any combination of these elements in your solutions, just to make sure that you are stabilizing those properly. But you do want to be careful with lead, because lead can drop out as the nitrate in higher concentrations of nitric acid. So you can kind of manipulate the order of additions to make sure to add your lead later on when the solution is more dilute, to make sure that you don't have these kinds of interactions. And the same issues exist for barium and cesium. So if you're adding those to your analysis, you want to keep that in mind as well. And then also lead can have issues in hydrochloric acid. So again, this is just a solubility issue. So you want to make sure to, if you have a high concentration of lead, you may need to increase your hydrochloric acid concentration as well to make sure that the lead is going to be stable. We've touched on issues with the mercury dimer a little bit in our previous slides, but I just wanted to go into just a little bit more detail on how this can cause issues in your working solutions. So here at IV, we take mercury metal and we react that with nitric acid, which forms the mercury 2+ ions, as well as nitrogen dioxide fumes, which are those brown NOx fumes that you see when the reaction is occurring. So what we do is we heat that with excess nitric acid to expel all of those fumes, because if we don't do that, and those fumes are left over in the solution, those can cause reduction of the mercury ions to the dimer, which will then disproportionate into the metallic mercury and the mercury 2+ when exposed to chloride or any other form of ligand. So just make sure that if you do have a dimer, or if you suspect that there has been formation of the dimer, that you go ahead and heat that with nitric acid, because that is going to convert all your mercury back to the correct form in solution, which is that mercury 2+ form. Do be aware though that if you have arsenic in your solutions, that this will also convert any arsenic 3 to arsenic 5 as well. We've discussed issues with mercury sticking to plastic components or plastic containers in a nitric acid only matrix. So one of the options that we presented was containing your solutions in glass instead of plastic. However, this is going to introduce some additional contamination, as glass is going to have quite a bit higher level of contaminants than something like LDPE or HDPE. So you want to make sure that you're looking at those and taking that into account, and looking at what your other analytes are in the analysis. Another thing that you need to consider is whether you have HF to stabilize elements in your solution. HF is caustic to glass, so if you do have to add HF to any of your solutions, then those cannot be contained in glass. So just make sure to keep that in mind when selecting your container material. To avoid any issues with mercury adsorption, we do recommend using HCl in the matrix if possible, as again, this is going to stabilize your mercury species and prevent any adsorption to plastic components. Another option is that you can stabilize your mercury with 1 ppm of gold trichloride. There's an EPA bulletin that I've linked here which describes this method, and we have used that in-house and found that to be successful for stabilizing mercury. But do be aware that that is still going to add chloride to your solution, so you want to make sure that if you're analyzing on ICP mass spec, that you are accounting for any of that interference by either using collision cell or by spiking that 1 ppm gold trichloride into your standards, blanks, and your samples to make sure that those are properly matrix matched. This is also going to cause issues with silver if you have that in your solutions, as silver will precipitate with trace chloride, and it will also make the solution photosensitive, so you may need to add some extra hydrochloric acid to keep that silver stabilized. Another issue is with thallium. So if you have thallium in the +1 oxidation state, it will precipitate with any chloride. So you want to make sure that you're using thallium +3 if you're mixing that with any chloride source. When selecting your sample preparation technique, it's important to consider both the type of the sample and which analytes you're interested in quantifying. Some sample types will require hydrofluoric acid to achieve a complete digestion, but HF can also cause stability issues with other elements that may be of interest, such as rare earth elements and some of your alkaline earths. In this case, you will need to determine which elements are important for your analysis and whether the addition of HF is truly necessary to achieve accurate results. We recommend a closed vessel digestion technique using microwave digestion for a Big Four analysis of cannabis or hemp. This will only require nitric acid along with a little bit of hydrochloric acid to stabilize mercury. Some samples may require hydrogen peroxide to achieve complete oxidation of all organic species, but this is generally not necessary for cannabis and hemp samples. Another thing to be aware of in your sample preparation is any source of contamination. So make sure that you're using clean sources of reagents, your acids, your container types, bottle types, the materials that you're using for your aliquots, anything you're using in the processing or homogenization of the samples. So again, preparation of method blanks is really going to help you determine whether any contamination is being introduced during your sample preparation. We also recommend avoiding any, especially metal containers, but also glass if possible, as these will be contributors of contamination. For cannabis and hemp, a small sample size is generally the recommendation, so about 1/2 gram for cannabis. So you want to make sure that your samples are as homogeneous as possible to make sure that you're getting a good representative sample of your entire batch. So this may require additional processing for samples that may be sticky or difficult to homogenize. So I've listed several methods here that you can refer to, but there's a lot of methods out there that you can analyze and see if those are going to be the most appropriate for your particular analysis. So for these next 2 slides, I'm not going to go into a lot of detail on the specific sample preparation techniques, but I did want to provide this information for you all to refer back to if you are having issues with a particular sample type. And we also have sample preparation guides available on our website that you can refer to by clicking on the links at the bottom of each element that are going to give you some really good tips and preparation techniques for each specific sample type. And this slide just gives the sample preparation methods for mercury and lead samples. Again, I'm not going to go into detail on these, but I did want to include these here so that you can refer back if need be. I've listed here some of IV's products that we've designed specifically around these heavy metals analysis. So the only stock product that we have that includes only the Big Four is our IV Stock 65, which was based around USP 232 pharmaceutical regulations. So you can order that on the website. The specifications are listed here on the right side of the screen for that stock product. We also can make customs, again, specified to your specific needs. We do have some customs included on the website at the link provided here that are based around specific methods for cannabis and hemp testing. I did want to mention that we have over 160 unique products that contain only arsenic, cadmium, lead, and mercury. So if you're looking for a particular solution that you don't see on the website, again, we can customize that to whatever your specific needs are. That will conclude this presentation. Please remember to check out some of the technical resources available on our website at inorganicventures.com under the Education tab. We also have a wonderful team of technical support chemists who can help with any technical questions or issues you're having with your analysis, so please feel free to reach out to us. Thank you for attending this presentation.